High above the Earth's poles, a silent sentinel stands guard, the polar vortex. It is a swirling mass of cold air, a giant cyclone that plays a vital role in shaping our planet's weather. This colossal force influences everything from the biting cold of winter to the milder temperatures of summer. We cannot see it, but its presence is felt in the chill of winter. The icy winds and snowstorms are all part of its grand design. The polar vortex is not a single entity, but rather a complex system with two main branches. These branches are interconnected, working in tandem to regulate the Earth's climate. One sits above the North Pole, the other above the South Pole. Each has its own unique characteristics and influences. Each vortex is like a spinning top, its base nestled near the Earth's surface, and its top extending high into the stratosphere. This vertical structure allows it to interact with various atmospheric layers. The polar vortex is always there, a constant feature of our atmosphere. It is a permanent fixture, though its intensity varies. However, its strength and behavior change throughout the year. These changes are driven by the shifting seasons and the amount of sunlight the poles receive. During the summer, the vortex weakens, becoming less organized as the polar regions receive more sunlight. The increased warmth disrupts its structure. Come winter, as darkness descends and temperatures plummet, the vortex strengthens and contracts, its frigid grip tightening around the poles. This contraction leads to more severe winter weather. This seasonal dance of the polar vortex, this ebb and flow of its power, has profound implications for weather patterns across the globe. From cold snaps in North America to milder winters in Europe, its influence is far-reaching and significant. The formation of the polar vortex is a delicate ballet of atmospheric forces, a mesmerizing dance that unfolds high above the Earth's surface. It is a testament to the intricate laws of physics that govern our world, a phenomenon that scientists study with great interest and precision. It all begins with the sun, or rather the absence of its warming rays. As winter approaches, the polar regions are plunged into prolonged darkness, receiving little to no direct sunlight for months on end. This lack of solar radiation causes temperatures to plummet dramatically, creating a stark and significant temperature difference between the frigid poles and the warmer equator. This pronounced temperature gradient is the primary driving force behind the formation of the polar vortex. Cold air, being dense and heavy, sinks as the polar regions cool, creating a downward movement of air. This sinking air generates an area of low pressure, which in turn draws in relatively warmer air from the lower latitudes. The Earth's rotation, however, complicates this process, preventing the warmer air from directly replacing the cold air at the poles. Instead, the incoming air is deflected by the Coriolis effect, forced to spiral around the low-pressure zone in a continuous motion. This spiraling motion, a direct result of the Coriolis effect, is what gives the polar vortex its characteristic and mesmerizing spin, a true marvel of atmospheric dynamics. The strength of the polar vortex is not constant. It fluctuates, sometimes dramatically, influencing weather patterns far beyond its polar domain. A strong polar vortex acts like a vigilant bouncer, keeping the coldest air bottled up in the Arctic. It spins tight and compact, effectively containing the frigid air within its grasp. During these periods, winters in mid-latitudes tend to be milder, with warmer air circulating freely. However, when the polar vortex weakens, the bouncer loses its grip. The vortex can stretch, become distorted, or even split into smaller, weaker vortices. This weakening allows the frigid air to escape its polar prison, spilling southward and bringing with it bouts of severe winter weather. Sudden blasts of Arctic air, plunging temperatures, and heavy snowfall can become more frequent and intense in regions unaccustomed to such extremes. The polar vortex and the Arctic Oscillation are often mentioned together, but they are distinct phenomena. Think of them as two instruments in a vast atmospheric orchestra, each playing a unique role in shaping our planet's weather. The polar vortex, as we've discussed, is a large-scale circulation of cold air centered over the poles. The Arctic Oscillation, on the other hand, is a climate pattern characterized by changes in atmospheric pressure over the Arctic. The Arctic Oscillation exists in two phases, positive and negative. During a positive phase, atmospheric pressure over the Arctic is low, effectively trapping cold air within the polar vortex. This results in milder winters for mid-latitudes. Conversely, during a negative phase, atmospheric pressure over the Arctic rises, weakening the polar vortex's grip. This allows frigid Arctic air to escape southward, leading to more extreme winter weather events. Section 5. A warming world and the polar vortex, a complex interplay. As our planet warms due to climate change, the delicate balance of the polar vortex is being disrupted. The polar vortex, a large area of low pressure and cold air surrounding the Earth's poles, is crucial in maintaining our planet's climate stability. While the exact relationship between climate change and the polar vortex is complex and still being studied, there is growing evidence that a warming Arctic is influencing the vortex's behavior. Scientists are continuously gathering data to understand these intricate dynamics. One theory suggests that as the Arctic warms at a faster rate than lower latitudes, the temperature difference between the two decreases. This phenomenon, known as Arctic amplification, is a significant factor in the changing climate patterns. This reduced temperature gradient can weaken the polar vortex, making it more susceptible to disruptions. A weaker polar vortex can lead to more extreme weather events such as cold snaps and heat waves in regions far from the poles. Another theory proposes that changes in the jet stream, a fast-flowing air current that circles the globe, are linked to a warming Arctic and a more erratic polar vortex. The jet stream's behavior is crucial in determining weather patterns across the northern hemisphere. The jet stream is driven by the temperature difference between the equator and the poles. This difference creates a pressure gradient that propels the jet stream at high speeds. As the Arctic warms, this temperature difference decreases, potentially causing the jet stream to slow down and meander. A slower, more meandering jet stream can lead to prolonged weather patterns, such as extended periods of rain or drought. These meandering jet streams can then interact with the polar vortex, causing it to weaken, stretch, or even split apart. Such interactions can have significant impacts on global weather, leading to unpredictable and often severe weather conditions. Section 6. Predicting the vortex's fury, tools of the atmospheric detectives. Predicting the behavior of the polar vortex and its potential impacts on our weather is a challenging task. However, advancements in atmospheric science and technology have provided us with tools to better understand and forecast these events. Meteorologists use a variety of instruments and models to monitor the polar vortex and its interactions with other atmospheric systems. Satellites orbiting Earth provide a bird's-eye view of the vortex, tracking its size, shape, and movement. Weather balloons, launched twice daily from locations around the world, measure atmospheric conditions at various altitudes, providing valuable data on temperature, pressure, and wind speed. These data are then fed into sophisticated computer models that simulate atmospheric conditions and predict how the polar vortex might evolve. While these predictions are not perfect, they are constantly improving, giving us a better chance to prepare for the potential impacts of a weakened polar vortex. Section 7. Bracing for the vortex's bite, extreme weather and its impacts. When the polar vortex weakens and allows Arctic air to spill southward, the consequences can be significant. Temperatures can plummet to dangerously low levels, breaking records and posing risks to human health, infrastructure, and ecosystems. Heavy snowfall and blizzard conditions can cripple transportation systems, shutting down roads, airports, and schools. The sudden influx of cold air can also lead to a phenomenon known as a bomb cyclone, a rapidly intensifying storm characterized by plummeting barometric pressure and hurricane-force winds. These storms can bring with them heavy precipitation, coastal flooding, and widespread power outages. The economic impacts of these extreme weather events can be substantial, disrupting businesses, straining energy grids, and impacting agricultural production. Section 8. Conclusion. Respecting the power of the polar vortex. The polar vortex, a silent guardian high above the poles, plays a vital role in shaping our planet's weather. Its strength and behavior influence the severity of winters, the intensity of storms, and the delicate balance of our climate system. As our planet warms, the polar vortex is responding in complex and often unpredictable ways. Understanding this powerful atmospheric phenomenon is crucial for predicting and adapting to the challenges of a changing climate. By respecting the power of the polar vortex and supporting the science that helps us understand it, we can better prepare for the challenges of a future where extreme weather events may become more frequent and intense,